Hello, Riles. I would like to do an example from 4.1. I would normally use this to start off 4.2. It's just a bit of a review of all of the definitions that we should have learned from 4.1. So if you haven't read the lesson yet, you probably should. Otherwise, a lot of this won't make a ton of sense. We are being asked to sketch 460 degrees in standard position, state the principal angle and the related acute angle, and then I've got a surprise for you under this piece of paper here. So, sketching in standard position, I need a Cartesian plane. That's how we're going to be dealing with angles for a while now, not just floating in space or inside a triangle, but on a Cartesian plane. In standard position, the positive x-axis is my initial arm, and positive rotations happen in a counterclockwise direction, just like the order of your quadrants go. Now, 460 degrees is larger than one full rotation. The lesson was changed to make sure it was clear that you are expected to show the direction and the entire rotation. How much larger than 360 degrees? About 100 degrees larger. And like that, somewhere over there. I'm not too worried about the precision of your angles. It should be definitely in the right quadrant. That's necessary, but it doesn't need to be super accurate. So yeah, without this like nautilus shaped thinger here, how was I to know that my curve didn't go in this direction? Or sorry, my angle didn't go in this direction? Or how do I know the difference between someone who did a full rotation and then went that far versus someone who just took a shortcut and went that far? So make sure you show the rotation and show the direction of the rotation as well. The principal angle is the angle that I would measure sort of the first time from the positive x-axis. The principal here means kind of most important, but also first as well. So if I go from the positive x-axis and I just rotate in a counterclockwise direction, and I measure the angle when I hit that terminal arm for the first time, that's my principal angle. My principal angle in this case, 460 degrees, is one full rotation and then a little bit more. I want to know how much more. I'll look at the difference between 460 degrees and 360 degrees, and that's 100 degrees. Now be careful with your symbols here. 460 degrees is not equal to 100 degrees. They're different numbers. They're not equal to each other. They share a terminal arm. They are coterminal angles. Right. The related acute angle, review your definition there, is the rotation to the closest x-axis. In this case, the negative x-axis is the closest x-axis. And if I've gone through 100 degrees and a half rotation is 180 degrees, then I know that my related acute angle is going to be given by the difference between 180 degrees and 100 degrees. In this case, the operation that you perform to calculate the related acute angle changes depending on what quadrant you are. But I wouldn't bother trying to memorize those operations. Just look at your sketch. This is not the first time in our course that sketches are going to be useful. Make sure you are always writing your units. All of our angles in this course are going to be measured in degrees. In advanced functions, you're going to be working with angles that are measured in degrees and angles that have no unit of measure. And there's a very large difference between an angle of 80 and an angle of 80 degrees. Look up radians if you're interested in a little bit of extension there. Now, one conversation that I'd like to have as well is why we don't measure to the positive y-axis. Often students say, like when you visualize 100 degrees, you're probably not seeing it as 80 degrees back from the negative x-axis. You're probably seeing it as about 10 degrees past the y-axis. So it's very, very common for students to accidentally say that the related acute angle of this of 460 degrees is 10 degrees and not 80 degrees. The reason why it's so important that we go to the positive x-axis will be shown down here. When I ask you to evaluate these ratios, let's pull out a calculator to do these. We actually only need a calculator to do 2 of these, or we'll only need a calculator to do 2 of these by the end of lesson 4.2. We'll just use a calculator for all of them today. The sine of 80 degrees, the ratio of my y value to my r value here, my sorry, my opposite to my hypotenuse. Looks like my opposite is pretty close to my hypotenuse in this case, so I'm expecting a relatively large ratio here. Sine of 80 degrees, yeah, is about 0.985. I wish they would teach trig ratios as percentages a little bit more in grade 10. This is saying that your opposite side length is 98.5% of your radius anywhere along this triangle. There's the idea of similar triangles as well. Does not matter how far out you go. Your opposite side length there is always going to be. If you're seeing some problems here calling this the opposite, then we'll sort of deal with those problems in lesson 4.2 with our new definitions. Let's go to the sine of 100 degrees. When I type in the sine of 100 degrees, which is my principal angle, I should not be surprised that I get exactly the same ratio. Because, oh, sorry. Well, we'll talk about this a little bit more in 4.2. I think what I shouldn't have been surprised by, I apologize, is the fact that the sine of 460 degrees is going to be the same as the sine of 100 degrees. These two angles are coterminal. Their terminal arms are in the same spot, so the ratios of opposite sides to hypotenuse sides are definitely going to be the same. But let's convince ourselves. I type in the sine of 460 degrees, and surprise, it's 0.985-ish. Okay. So these two coterminal angles have the same sine ratio. They're also going to have the same cosine ratio and tangent ratio. We'll see that for the cosine ratio. The sine of the related acute angle is related to the sine of the principal angle. Is it always the same? Let's find out. Let's start over here with the cosine of 460 degrees. Now this might be new for us here. We have a negative ratio. In triangles in grade 10, how could the ratio of the adjacent to the hypotenuse ever be negative? When would we ever have a negative side length in triangles? We're going to have to stop thinking about trig as being related solely to triangles in 4.2. Since 100 degrees is coterminal to 460 degrees, I'm going to even lock this in, and then I don't think I'll be surprised when I calculate the cosine of 100 degrees, and hey, look, it's also negative 0.17. As a percentage here, we're saying that the adjacent side is about 17% of the hypotenuse. And just watch what happens here if I calculate the cosine of 80 degrees. 80 degrees is an acute angle. Most of the trig that you did in grade 10 was for acute angles, and most of your ratios were positive. The cosine of 80 degrees is not equal to the cosine of 100 degrees, but it is related to the cosine of 100 degrees. It is not as clearly related to the cosine of 10 degrees, or, which is why it's so important for us to go to the closest x-axis. So if you were to ask me how are related acute angles related to principal angles or initial angles, I would say that their trig ratios have the same absolute value. And by the end of 4.2, we should be able to predict why these signs are the way that they are. S-I-G-N-S, not sine, S-I-N-E. Okay. Try out lesson 4.2. We'll introduce some new definitions there and take a pretty big step towards some new trigonometry.